Good afternoon, everyone, and welcome. Everyone can hear me okay? Cool. So, a quick show of hands. How many in the audience have heard of GDPR? Very good, very good. How many in the audience work for companies that are impacted by GDPR? All right. People who have their hands down, you just don't know it yet, you are impacted. And then finally, how many people in the audience think that their companies have, everything in place? They've got all the systems and processes in place, and they're going to be compliant on the day. Okay, at least we're in the right room. So we've been on this journey for the last 6-7 years working with data. I actually joined in 2010, and I've kind of seen a lot of foundational technologies emerge around LinkedIn as well as from LinkedIn. And today we'll talk about kind of how we've dealt with both the data democracy problem statement as well as kind of the data privacy problem statement, and kind of think about how we can solve for both of these together. All right, so first let's look at the compliance landscape. It moved forward on my computer, but let's try that again. All right, perfect. So, in the human era, there have been 3 big revolutions. Revolution 1 was, the agrarian revolution. We learned how to grow crops and then, maximize food production. Then came the industrial revolution, and we learned how to make giant factories and churn out goods. And then right now we're living in the 3rd one, which is the digital revolution. And the top curve right there is the pace of digital innovation as it has happened over the decades. 1980, that's when the PCs came out, and that changed everything, right? A decade later, the internet was born, and that changed everything again. LinkedIn was born in 2003, about another decade later, and that at least gave the world a really good professional network where people could find each other, connect, and be found. And around the same time, a lot of different social networks came up. And then the iPhone was born in 2008, and that again changed everything, right? So we've been changing things every 10 years. And this rate has accelerated in both the amount of data we collect as well as what we do with this data. And at the same time, data protection laws have tried to keep up with this innovation. And we're all looking up at this giant peak called GDPR that's coming up, significantly larger rights, and significantly more complex to execute on. And we'll talk about some of the things that we're doing to kind of handle this compliance problem at LinkedIn as well. So I hope everyone knows what LinkedIn is. Our vision is to create economic opportunity for every member of the global workforce. We have 500 million members, a lot of companies, a lot of jobs, a lot of endorsements, and a lot of schools. So it's a giant economic graph with a lot of connections, and a lot of value is derived by mapping what happens in the real world, where you connect with people, you find jobs, you like a company, you follow a school, or you were at a school, you're trying to acquire a new skill, and then digitizing that and making it provide value for the member. However, this leads to this kind of paradox, like who here joins LinkedIn because they want to stay private, right? I mean, it's a network where you join because the value is in joining, the value is in being found. But at the same time, you're entrusting LinkedIn with a lot of sensitive or confidential data. You're importing your contacts, you're entering sometimes your salary, we have some products around it. And so we have this paradox that we have to keep solving for. How do we ensure that members are getting what they need out of the network while preserving the privacy of the data of the members that they're giving to us as LinkedIn? Thankfully, members first has been one of our core values since we started. I mean, the day I joined, I was hearing this thing being mentioned again and again, members first. We don't refer to our users as users, we call them members. We feel like they're part of the family. And members first is a core value at LinkedIn, and we use the data that they give us to actually make things better for them. A simple example is, if you're well connected, then you've got a lot of inventory. We can show you a lot of stuff because people in your network are sharing a lot of things. And so we use data to make sure that what you're seeing is what you find useful based on what you've interacted with in the past. However, if you have very few connections, then we're going to try to pull in inventory from other places so that you can see more stuff, discover more things, get surprised by content that you didn't anticipate. So, our member value is proportional to how much knowledge we get. But member privacy at the same time is super important. And we continuously strive to maintain this fine balance between providing enough value and then keeping enough privacy. So let's look at what the data pipeline looks like at a high level. You've got a mobile app and you've got LinkedIn on it. And it's, as you work with the app, as you click on things, as you view profiles, it's sending data. We call it member data. In the GDPR terms, it's personal data. And it gets sent to LinkedIn. But LinkedIn is not one thing. There are a lot of front-end servers. They're aggregating this data. There are databases that are involved. But it all gets kind of unified into a professional knowledge graph, if you will. And we call it by many names. Some call it the unified data layer. Some call it the professional knowledge graph. And we build systems of intelligence that work on this data and build intelligent models that can then improve the member experience. So that's what we talked about. But at the same time, we are trying to figure out how to make things better in aggregate. How are products being used in aggregate? How are new products being built? Are new features getting the same kind of traction that we think they should? And how do we tweak those so that people work with them better? And those lead to business decisions. So we're making both member improvement suggestions back into the website or the mobile app. And we're also using the same data to make better business decisions. And that, I think, captures kind of the problem statement. You've got kind of a combined data set that you're using both to power the members' experience, but you're also using that to improve LinkedIn as a business. So on the one hand, when you start out with this member value proposition, I have to continuously build data products that improve the lives of members. We first said, we need data democracy. And our data scientists, we incubated the data science term at LinkedIn. And our data scientists have, from the beginning said, we need data democracy, which is, all the data all the time. So what are these needs? I want to analyze as much data as possible so my results, my models are accurate. I want to discover data that I need to use for my analysis as easily as possible. There's a lot of data out there. I want to make sure I can find the relevant data sets quickly. And then when I find something, I want to access it easily. I want to be able to process it using tools that I'm familiar with, tools that I like, so that I can build my analysis quickly and then improve things. At the same time, we have the data protection kind of hat where we want to make sure that LinkedIn members' needs are met. Right? And so what are their needs? They want to make sure that their personal data is stored only where needed and not propagated unnecessarily into lots of different systems. A member, they would want their personal data to be deleted when they close their account or request that their data be deleted or a specific subset of it. And they also want their personal data to only be processed if it's essential to process it. And also in many cases, only if they consent to that processing in the first place. So there are a lot of these needs. And they actually lead to this paradox between data democracy and data protection. On the one side, you have the need for more data, the need to discover this data, and the need for easy access to these data sets. And on the other side, you want less data. You want to discover violations, not data. And you also want to restrict access as much as possible and processing as much as possible. So, that's kind of the big challenge that we face, and I think many people in the audience also are facing, many companies. And what I'm going to try to explain to you today is how we've solved this problem. It can be solved, and how we ended up kind of solving it piece by piece and kind of putting it back together. But first, some context. What does LinkedIn data look like? So this is the big LinkedIn data ecosystem. It's a giant, complex beast, and I try to simplify it as much as possible so it could fit on a slide, but even then it's a lot of stuff. So I'll gently ease you through it. Step one, we've got our members, our customers. They're coming in through the desktop or the mobile apps. They're using their browsers or the mobile apps. And they're interacting with LinkedIn. And LinkedIn is basically a bunch of services. We're service-oriented or microservices architecture. There are a bunch of services that are in the back. But for our internal business-facing insights, we also have internal apps, which are often built on a similar stack. It's not the same service, but they're built using, engineering builds these services. And in this case, employees are accessing this data through these apps and services. So let's look at the data footprint of these services. These services are writing data. When you write data, typically you need to store it somewhere. The first thing you need is a database, right? So we have a few. We started with Oracle and then moved to MySQL and then built a whole new distributed database called Espresso. And so all our data pretty much lives there. That's kind of our scalable database story. And these databases are, getting ETL'd out into an ecosystem of Kafka and Hadoop. They're also streaming change logs out, where possible, into Kafka. So we have a nice mix of streaming changes coming out from all of our databases. And we also have incremental snapshots and dumps that are coming in. At the same time, the same services are actually emitting events. So when you view someone's profile, that's a tracking event. That's a business event that happens. And we want to track it. It's not in any database. And so those services are emitting events. A lot of people call this logging. And we call it events because we want to think of them as structured logs. And these logs go into Kafka as well and then get ETL'd into Hadoop. So as you see, the data footprint coming out of these services is going into a combination of databases and Kafka and then getting ETL'd into a combination of Kafka and Hadoop. So that's kind of our data warehouse, if you will. It's kind of a combination of a streaming ingest platform plus an at-rest layer that's useful for crunching data at scale. And then inside this particular platform, you've got all of the analysis work happening. You've got data standardization, reporting, machine learning. Some of it is streaming, some of it is batch. But in aggregate, it's all happening on top of this combined layer. And the results of these computations are sent back up because, data never goes to die anywhere. It kind of gets reborn. You create derived data sets, and then you have to do something useful with them. So these derived data sets can get loaded up into systems that are optimized for serving. So these could be key value stores or analytics stores or search indexes or graph indexes. And in a lot of cases, we've built both streaming pipelines to ingest data into these systems as well as batch pipelines for bulk loading data into these systems. So from the combination of Kafka and Hadoop-based ecosystem, we're ingesting in derived data into our serving ecosystem. And these are optimized for kind of the read patterns that we need. And then the same services that I talked about earlier are reading these insights. Sometimes these are insights, sometimes these are recommendations. And these services are, basically now completing that whole feedback loop. So you're back to kind of the zoomed out picture of a service that is emitting data. Data goes all the way out to Kafka and Hadoop. Derived data gets produced, gets pulled back, and then the service becomes more intelligent. The system becomes more intelligent. And we use the same patterns for our online systems that are facing LinkedIn.com, as well as our internal systems that could be internal insights or experimentation or any other business decision-making product. All right, so now that you know about LinkedIn's data ecosystem, let's talk about how we handle the data paradox. Step one is solving for more data and less data at the same time. So to first solve it, you first need data. So step one is usually more data. And as I told you, we had these big data hubs at LinkedIn, Kafka and Hadoop. We run them at pretty large scale, multiple trillions of messages and lots of machines. We are not on the cloud. We actually run our own data centers. And pretty large numbers. But I think a lot of startups, even when they have, they're in their infancy, they're starting to adopt a similar kind of pattern of having Kafka as their streaming layer and Hadoop or S3 as kind of their storage layer. So once you kind of build these data hubs, you realize that you have to get data in and out of these systems, right? Because these are where all the data has to come in and go out of. And the good thing is Kafka and Hadoop are actually very accessible. They have clients in every single language that you can think of. And so it's very easy for an analyst or anyone to write up a little script, ingest some Twitter data, write it into Kafka, ingest some Facebook data, write it into Hadoop, add in some other APIs while you're at it. And most companies start evolving that way. We did the same. We had lots of different pipelines that we were integrating data with. And every single team would kind of do it their own way. Some would do it in Python, some would do it in Java, some would do it in Perl, and some would do it in Bash, because that's cool too. And what we realized was each one of these systems had their own little flaws. Some system would be really good for data quality, but would lose data once in a while. Some system would be really good at scale, but wouldn't really have good auditing or data quality built in. And so we were, instead of fighting like the real fight of making data better, we were fighting kind of the fires of lots of different pipelines, and they're all breaking in very different ways. And so we decided to kind of centralize a lot of this work and build kind of a unified platform that could do all these kinds of data integration needs that we were facing in one system. And so Apache Gobblin was born out of that need, the need to understand that data is neither stream nor batch, but kind of a fuzzy mix between the two. There are cases where you want to ingest data in a stream fashion. There are cases where you want to ingest data in a batch fashion. There are lots of different sources and sinks. And over the years, we've kind of unified a lot of these ingests into one single framework. And at LinkedIn, it drives pretty much 80% and higher of our data ingest. These are all hard problems at large companies because killing each pipeline is hard. It's working. It's not broken yet. Why fix it? So there's a big amount of work, and Charles is smiling there because he's lived through that life at Netflix. It's a lot of work to take a central thing that maybe is better than everything else out there and then get it to actually be 100% of everything. So we're at 80+%, and we're pretty happy. And it also does all of our Hadoop to Hadoop moves as well. So there are a lot of interesting sources and sinks that we've built over the years. We've open sourced it as well. It's actually an Apache project. Earlier this year, we incubated it. It's still incubating. And out of all of the different systems that are out there, what is unique about Gobblin is that it actually does stream and batch well. There are a lot of data processing systems that are starting to do stream and batch together. Gobblin is optimized for the ELT pattern versus the ETL pattern, right? Where when you try to get data from one system to another, don't try to transform it too much before you get it to the other system, because you'll make a mistake, and then fixing it is actually sometimes more work than first copying the data and then fixing it. So it's generally, there are certain design choices we've done that are around kind of that pattern that we've seen mostly around big data integrations. So if your data warehouse is a few million records and you can probably live inside a Postgres, then don't think about it. But if you're doing large-scale data integration across lots of different systems, then it's a great tool. A lot of big companies, of course, are using it. Prezi actually is adopting it as well. And there are all of like small companies who've taken it and are running it in the cloud. So it's a pretty exciting project. So we did more data. We got a lot of systems connected together, and we are able to now move them back and forth between our data hubs. So how do we solve for less data? So what are the requirements for less data? I don't know if you're familiar with all of the GDPR docs, but there's this thing called right to erasure, or also known as the right to be forgotten. And this is kind of a very small snippet from a very long paragraph about what it means. And it's complex. And when we looked at it as an engineering team, we didn't quite know what to make of it. So we sat down with our lawyers and said, please explain this to us. And then we kind of finally came up with an engineering version of this, which is, find data about members, LinkedIn members, and have the ability to delete it, or a subset of it, depending on what the member really wants, from all of our data systems. So that's kind of the less data problem. And I don't know if you remember from the data ecosystem, there's a lot of data that finally comes into Hadoop. A lot of the intermediate systems are really transitory, so data doesn't live there very, very long. Data comes into Hadoop, and then a lot of derived data systems are actually produced from Hadoop. So Hadoop is actually like a big data sink where a lot of data lives on for very long. And so that was kind of the first thing that we went after solving for, data deletions on Hadoop. And it's actually quite hard because there's a lot of data and a lot of different formats. Hadoop is very open, so a lot of different people can bring in data, very different formats. How are you going to actually find all of this data and then be able to delete it in the appropriate way? So these were kind of the needs that we thought we were seeing. Whatever system we chose, it would need to understand how HDFS data was laid out at LinkedIn. How were people organizing these data sets? How were they partitioned? What were the formats that were being used? They needed to kind of, our lawyers told us we had some leeway. We didn't have to delete it the instant the button was clicked. We had some amount of time before which all the data had to be gone. So we could cycle kind of asynchronously through all of these data sets within an SLA and delete all these records without affecting any running jobs, obviously. You don't want to have a job that was kicked off, then suddenly die because the data that it was operating on disappeared from under it. And then, some of the other things we realized was, what if we get it wrong and we delete a bunch of stuff and realize we actually made a mistake? So the ability to quarantine records, exceptional records or exceptional situations. I deleted a lot of data. Maybe that's okay, but someone needs to check. And also being able to scale to processing this kind of large scale of data. And so the team that was tasked with solving this problem was actually the same as the team that was ingesting all of this data. So I kind of said, can we look at Gobblin and kind of try to see if we can use Gobblin to solve the same problem? And to understand how we kind of went about it, you first have to understand a little bit more about Gobblin at the next level of detail. So the logical pipeline of Gobblin looks something like this. You've got a source, which is a system that you're ingesting data from. The source is typically parallelizable, so the extraction of data from it can be split up into partitions or work units. And for each of these work units, each unit of work, it could be a Kafka topic partition, or it could be a file split in Hadoop. You basically have a tight loop of an extraction, the ability to convert the records that you're extracting into something else, the ability to check whether the quality of the resulting record meets your goals, and then finally the ability to write into the destination. And in some cases, if you want to actually hold your horses until all of the ingestion is done and then do an atomic publish for systems that can support that, there's a final phase called the data publish. So for systems that allow you to do atomic renames, atomic transactions, we use it quite a bit. So that allows you to kind of do end-to-end ingestion at scale with the ability to parallelize and also have a little bit of control over how you're transforming each record as it comes in. So you take something like this and say, okay, how do I tweak it to be able to do data deletion? Well, if you look carefully at the task pipeline, there's a source, so we can make that HDFS. So we're reading HDFS data back. And each work unit now gets executed on the standard extract, transform kind of pipeline. And within that, I could write a converter that basically looks at a record and is able to look at any deletion requests that have come in the meantime. So a member might have said, delete my search history, right? And I'm looking at search history data. I found a record, it's for this member. I'm able to look at this member's delete request and decide, oh, I need to drop this record because this member has requested a delete. So if it needs a purge, I can drop it. I didn't have the time to draw the ability that Gobblin has for creating forks. So I can actually not just drop this data, I can pass it down a fork and then quarantine that data off into a separate area. So that then allows me to extend this system pretty simply for Purge. And I get all of the scale benefits, I get all of the understanding of the HDFS organization, which anyway Gobblin has to do. So that's what we did. So Gobblin is kind of going from not just data ingestion or integration to data lifecycle management. You ingest data, but you also manage its lifecycle. You're able to purge it, you're able to compact it. And the number of data sets that it manages are in the many thousands, multiple hundreds of terabytes scanned per day. And it leads to kind of an open challenge that we're observing. A lot of these decisions that were made early on about HDFS, S3 was immutable data. And so we've got a lot of immutable storage formats. But then we've got all these fine-grained deletes coming in. and it really makes disks very unhappy. I was explaining this to someone the other day, and in kind of a non-technical way. And the closest analogy I could come to was, imagine you have a haystack, right? You've got a haystack, and you're looking for a needle. But then you don't want to just look for the needle, you want to remove the needle from the haystack. So okay, problem 1, find the needle. Problem 2, remove the needle from the haystack. Except the haystack doesn't like needles being removed from it. So what you have to do is move the haystack one straw at a time and leave the needle behind. So that's really what's going on under the hood. You're processing a ton of data, you're reading all of it, and then you're leaving the stuff that you don't want in your final state back somewhere, and then you're creating a new data set really, which doesn't have the data you wanted deleted. So it's painful, and I hope, and I think we're working on some of these things internally as well, that we can see some improvements in kind of the storage formats so that they allow for this kind of fine-grained deletes all the way down in the storage format itself. All right, so how did we solve the more data, less data paradox? We built a standardized data integration framework, moved all our data to it, and then built data lifecycle management into it. Challenge 1 done. What was challenge 2 again? It was the ability to discover data and at the same time also discover violations. So what do we mean by that? Let's start with discovering data. This was the data ecosystem that I talked to you about. A lot of our initial focus was on making analysts and data scientists very productive, and that means focus on where they're at, right? So they're mostly working on Hadoop. We also have Teradata, so there's Teradata hidden in there as one of the derived stores that feed from Hadoop. And so we focused on making discovery easy in that ecosystem. And so step 1 was just a basic metadata-based search experience for data scientists. So you come to a central portal, you type in a data set name, boom, you get a few results, some from Teradata, some from Hadoop, and then you do what you need to do with it. And so these were the 2 questions that we started with. Where is this data, and how did it get here, or how did it get created? And those 2 names, those 2 questions were used to form the project called Warehouse. It was also a pun on the team that was working on it. It was actually the Warehouse team that was working on the problem as well. So it has led to lots of problems. We can no longer talk about the Warehouse team without people asking, wait, which Warehouse team? But anyways, the name has stuck. And what we use Warehouse for is to find data and then navigate relationships between data sets. It's been in production since 2014. Most of the users are data scientists as well as product engineers who are building products. And the use cases tend to be discovery for analysis, but also impact analysis because I'm changing something. So I'm an engineer, I produce the page view event at LinkedIn, and I'm going to add a new field or I'm going to deprecate something, and I want to know who's getting affected because of that. And I want to be a good citizen. I want to find all the downstream consumers, send them a note, hey, this is going to change. So a lot of impact analysis workflows get powered by Warehouse as well. Like most LinkedIn projects that aren't core and aren't proprietary, it's also open source. There are a few small startups that are actually using it. I know Fitbit uses it. So it's getting a little bit of interesting traction. We actually did a big rewrite recently, and we're enhancing it for a lot of GDPR-related compliance problems as well. So there's a lot of excitement to see how it can be used for general purpose GDPR compliance versus just for LinkedIn. So it'll be cool to get your thoughts on it as well and feedback if you're dealing with similar problems. So what does Warehouse look like? You can search for data sets, metrics, and flows. So those are kind of the things we index. And once you search for it, you can refine by the type of data store that you really care about. And once you find something, you can see who the owners are. You can ask them a question. These people did not want their identity revealed, so we care about their privacy as well. So these are all redacted names. Once you do that, you can also look at the schema of the data set. There are comments. You can ask questions there as well. And you can also look at lineage. Lineage is something that's cool to build. It's very hard work the first time you build it because no one really wants to integrate with you as a first-class citizen. You're just trying to prove that lineage is a good idea, so you go and scrape every single backend you can find, and you're reverse engineering all sorts of bad stuff. But the team went and reverse engineered Informatica, which was easier. They did a bunch of integration with Pig and Hive, and then also our Teradata SQL scripts. So depending on what kind of information we have, you can actually double-click and inspect code and things like that. For most of our popular data sets, the lineage graph actually becomes super hard to visualize itself. And it's actually a data visualization problem. And we've done some work on it, but I'm not proud of it yet. It's work in progress. A lot of people get down to actually querying it by the API and getting kind of downstream data sets because they want to do something programmatic with it. All right, let's talk about discovering violations. So we discovered data, good. That's kind of easy. It's kind of a 80% problem. You do enough, you cover enough data sets, people are happy enough, and you say, okay, I'm done, right? I'm improving productivity of people because they can mostly get to what they need. But discovering violations is a much harder problem statement. What are the things we're talking about? We're talking about things like, hey, what data sets at LinkedIn contain PII or highly confidential data? How many of them contain member-to-member messages? Because that's like a super critical and private data set. How many of them are accessible by a certain team? And how many of them have been accessed by that team, right? And then when it comes to data deletion, have they been purged within a particular SLA? Am I able to actually guarantee that we are in compliance? So being able to discover these sort of violations means you have to answer much harder questions. It's no longer, yeah, if we mostly got you there, you're good, right? We have to get the answers absolutely right. And that means we need wider and deeper metadata. So what do I mean by that? We need metadata about lots of more systems. So it's not just 2 or 3 systems, it's actually more than 20. We did an inventory recently, and that number, every time I look at it, I find another system that I did not know LinkedIn was running that's in there. And now we have to integrate with that as well. We have to understand what data is in there. And these are NoSQL systems, these are SQL systems, sometimes these are indexes, sometimes they're blob stores. And so it's a big, diverse ecosystem. And then within each data set, we need deeper understanding. We need to understand, not just the physical, whether it's an int or a long or a string, but whether it's member-to-member data, if it's an email address, if it could contain a member ID, right? So we need to understand semantics at a deeper level. So that's kind of depth. So we need wider metadata. We also need deeper metadata. And so at a high level, this is kind of what we did with Warehouse. It's kind of what we call a metadata refinery approach, where we try to give you clean interfaces, and we tell you, please publish to those interfaces. So, we think about metadata in 2 forms, and I think these are fairly standard ways of talking about metadata. There's technical metadata, which is like catalog. What are the data sets? Where are they at? What's the schema for the data set? It could also include things like what scripts are running on these data sets. And then there's operational metadata, which happens when you actually run something. So, a data set got ingested. This partition got ingested right now. This data set was accessed. So it's kind of what happens when there's activity happening on the system. And that's kind of operational metadata. And all of these are getting plugged into kind of a general purpose metadata bus, including Kafka and Hadoop. And then brought back into a centralized repository of metadata, on top of which internal employees are coming in and asking questions and doing their analysis on the metadata, right? And in the act of doing that, they add annotations. They say, hey, this is actually a reputable data set. We should use this more. They add comments and enrich the metadata in ways that the source systems cannot. And at the same time, we have a ton of data as well. We've got data along with the metadata, and so we can make certain, we can have machines understand some of this data and make predictions that sometimes humans make mistakes with, right? If I ask someone to annotate a data set with 100 columns and expect them to get it right every single time, they get it right most of the time, but sometimes they're not sure. This column may contain email addresses, I don't know. So we throw machinery at the problem, and essentially these models and these classifiers are running on the data, samples of the data, and generating recommendations for what should the metadata look like. And those refinements then get, again, socialized and surfaced back into the UI. So if you draw the metadata data flow, which is a mouthful, it actually looks like this, exactly like LinkedIn's data ecosystem. So, and that's kind of the key to making sure that metadata scales. Your data flow should look exactly like your metadata flow and vice versa, because metadata is just data about data. So you've got data systems that are publishing metadata into Kafka. That is getting ETL'd into Hadoop. Sometimes we have snapshots and incremental dumps of metadata coming into Hadoop. We have machine learning on top of this metadata, as well as samples of data that then generates derived data sets, which are serving structures for metadata. Some of these are key value stores. Some of these are search indexes. Some of these are column stores because we want analytics on the metadata. And then it's being surfaced back into the warehouse application, which is an internal app built on top of this data set. So there's a unified kind of metadata data set in Kafka and Hadoop, and then an application built on top of it that makes it super easy to work with this. But if you wanted to run a Presto query on this metadata, go for it, because it's all there in Hadoop. If you wanted to set up anomaly detection on this metadata, use the anomaly detection tool we have, because metadata is just data. So that's kind of a thing that we've kind of got into over the years, but I think it's super powerful. I think we should always think of metadata as data and not hide it in some one MySQL instance, because you're going to regret it very soon. All right, so we solve for the discover data and discover violations problem by kind of building a standardized metadata ecosystem. And that's challenge 2. And challenge 3 that we had was being able to have easy access to this data, as well as being able to restrict access to the same data. So how do we do that? Well, first, like most things, we want to give people a lot of freedom. And our data scientists, we gave them a ton of transformation engines to work with. Some of them work better on streaming systems. Some of them work better on batch systems. But that's the soup of systems we've got. Samza, Spark, Hive, Pig, Scalding, MapReduce. Presto is coming in as more like an interactive analytics engine rather than like a thing on which you build ETL pipelines on. So I didn't quite put it there. It's available as a query tool. And then you've got the data hubs, the in-motion and the at-rest data kind of as a standardized data warehouse. And there's a lot of freedom of expression. As an infrastructure team, we try our best to keep this set small. But we also try to make sure that there's enough variety, because some people like writing code in SQL, some people don't. Some people are actually writing out, they like types, so they might want to drop down into Spark or Scalding. And so we've tried to keep that flexibility for different use cases. But that actually leads to problems. HDFS makes it super easy for you to create raw data and then quickly share it with people. So we had people with CSV data sets, binary JSON data sets, Avro, but partitioned slightly differently. My Avro partitions are not quite the same as your Avro partitions. And then once you've shared a data set and you've exposed that folder, or the fact that you drop data into that folder every day, people start creating dependencies, and the dependencies get hard-coded. All of these individual systems start accessing this data using the native readers. So I'll have the Spark Avro reader reading this data, or the Hive SERDI reading it, or Pig will have its own little Avro storage format. And so that was like level 1 problem statement that we were dealing with as infrastructure providers. We standardized on Avro pretty early in LinkedIn's evolution, and that led to a lot of good things. But it also led us to realize later on that, wait, row-oriented is really good for streaming data, but column-oriented is awesome for analytics. So as the new column-oriented data formats like Parquet and ORC were coming out, we were going, oh, wow, let's transform all of our Avro data into Parquet or ORC, whichever wins, and then have everyone use it. Wait, how do you do that? Either you call time on a particular data set, tell the analyst, don't run your scripts on it today, we're converting it to Parquet, and then tomorrow go change your reader, which was earlier reading data using Avro, to be Parquet, and then you're good, right? That's one option. The other is you make copies of the data, so an entire copy of your warehouse in a different format, and then you move everyone to it. Both of them are super expensive. So it's really hard to move to better formats without breaking everyone or copying data twice. The second thing we were dealing with were semantic challenges. So it's not just about formats and how data is organized, but data is also always unclean in some way or the other. On certain days, there was bad data, right? And I can't really fix it up because it's there. So I go and tell all the analysts, hey, data for these particular days on that particular event is bad, so please accommodate for it. And they go and make their little changes to their scripts to make sure that they're not reading that data or compensating for the numbers there. And so that leads to a lot of duplication in the code on the analyst side. And data models are also in constant flux. There was cases where we were moving from one style of producing events to a different style. And that meant all the downstream code has to change. Earlier, we were producing to a generic event, and then we moved to emitting to very specific events and splitting up our event taxonomy. That means everyone has to change. And we looked at our kind of online friends, the people building services, and we're like, why are they happy? Why are they not in the same kind of problem as we in the data world are? And I think that's because data never has had the same amount of focus on interfaces. I mean, we have schemas, but we don't really have much beyond that. And so what our take on it was that we need microservices for data. It's not just about having a schema, but it's about having some amount of buffer between the schema and the producer and the consumer so that you can actually have some logic in there to manage this evolution of data that goes through. And databases have had views for a long time. And a lot of people have used views successfully and then got burnt once they got too successful. But views, if done in a controlled manner, can actually solve a lot of these problems. But they've never really been done consistently for Hadoop. And that's what we set out to do. And we built this project called Dali, which stands for Surreal Attempt at Trying to Solve This Problem, but also stands for Data Access Layer at LinkedIn. And we built it to basically abstract away all of our physical data, add in the ability to add views on top of this data, and then make it accessible to all of the frameworks that we have. So this is what it looks like. It's gory. It was a lot of work. We got, a lot of people know that Hive has SerDes that every system can integrate with, but it doesn't allow you to execute views within that. So we had to do kind of a lot of extra work to make views also work within this ecosystem, and then make it work across all of our ecosystem. And then now what we're working on is actually making this work on Kafka as well. So we've got Hadoop and Kafka and then Dali data sets sitting on top of it, and our entire ecosystem of processing frameworks are able to use Dali as the access layer for accessing all this data. So what does this mean for our access restrictions problem statement? So we've got access to data, we realized some problems, and then we solved for it. But access restrictions on data are kind of a next level of problem. They're kind of basic requirements like prevent access to this data because this person does not have any business need for access to this data. That's kind of easy. You have folder level access or table level access. Then you have privacy by default, like analysts should not get access to raw PII ever by default. And then there's the next level, which is consent-based access. An individual member can say, I do not want this part of my data to be used for this purpose. So how do you do that? For step one, all you need is the raw data set, a name for it, and the schema for it. And then you can say, well, this person does not need access to this data, I'm not going to allow you. But then to get the next level of information, you need metadata. So I need to know that this is the profile data set. I need to also know that that particular column is the member ID. It's not just an int. I also need to know that these other two columns are name fields. And then I also need to know that name is PII and member ID is PII. And then I can use that to control some access. But that's not enough. Remember, I talked about having this ability for a member to control access to data. What does that look like? I've got a bunch of data elements. I've got profile data. I've got my email addresses. I've got address book. And I've got these use cases that LinkedIn has. Some of it could be optimizing my world. Some of it could be optimizing LinkedIn's world. Some of it could be sharing data with third parties. And I want the ability to have fine-grained control over this data sharing. So it thinks, if you look at it as a data geek, it looks like a giant bitmap, right? You've got kind of a giant bitmap per member. So that's what we did. We took this entire privacy data set, preference data set, and made it a data set called the member privacy preferences data set. And now with these three things, the raw data set, the metadata, and the member privacy data set. If you have access to all of this through a single reader interface, you can actually do interesting things. If you have processing logic and you know why that processing logic is trying to access the data, because it gives you the use case that it's running for, then as a Dali library, I can say that given this data set, given metadata for it, and given the use case for which data is getting accessed, I can generate all of the transformations on the fly. I can obfuscate data, I can null out data, I can join with this member privacy data set to make sure that I'm only showing you data that you have access to. And that leads to kind of this ability to do all of these access restrictions at all these levels using a single thing. And that's pretty cool. We're still kind of putting the final finishing touches to this, but we're pretty close to getting there. And once you add in the delete request that the member has provided, you actually get an instantly clean data set that you can access at all times, which includes both access compliance as well as complying with any delete requests that have come in. And then you put Gobblin on top of this, and then you can materialize these data sets. And that allows to actually get Purge for free. So you can actually purge by just materializing the Purge use case. So we're kind of getting pretty crazy about this and integrating the Dali access layer and doing a lot of these access controls in there and kind of having compliance baked in to this access layer. So that's how we solved for the third challenge. And that kind of solves this data paradox of, metadata at the foundational layer, feeding up into data lifecycle management and the data access layer. We've built projects that are open source, Warehouse and Apache Gobblin in particular. Dali is something that we've wanted to open source for a while. I think it'll eventually get there. We're working on it. And since a lot of us are actually solving similar problems, it would be great to actually collaborate and work on these together. But technology is just part of the solution. There are a lot of process pieces that we put in place. Privacy by design is a big part of this. A lot of the products, when they get built in, have a review process where we go into privacy. When data models get designed, there's a review process. When new regulations come up, we sit down with the lawyers and we have extended sessions where we try to understand what it means for our technology. And a lot of the GDPR-related work came out of that. And then company-wide, LinkedIn has had this culture of being able to execute horizontal initiatives where I can actually scale the acquisition of metadata, or I can scale the paying down of tech debt on a particular infrastructure piece by sending out these massive 20% tickets to the rest of the company and then get them to do it. And that has actually worked really well for some of these centralization pieces. So key takeaways: the beast is real, compliance is here to stay, it's getting stricter, and it's getting harder to implement because as we use data in harder and harder ways, it becomes harder and harder to keep that data private. However, I think we have a blueprint that can make it work. Privacy by design is obviously a big part of this, but you also need to standardize on some important pieces in your data infrastructure stack. The metadata piece, the access layer, the lifecycle management piece. If you try to do them again and again, it's a hard problem, and doing it multiple times is just going to make it harder to solve it in aggregate. And finally, the entire company needs to be bought in. It cannot be something that a small team does. Everything has to be aligned across different organizations. We're talking to teams that we didn't even know existed to make sure that we can actually get this whole thing working. So that's kind of the end. I didn't realize, but I ran out of time. We can take a few questions or not, depending on what the organizers decide. But I'll leave this slide up and then see if there are any questions.
Yeah, we'll definitely do some questions here. First, I wanted to give you this. Say thank you for coming and telling us our story, your story.
Thank you so much.
All right, so we'll start with first one here. According to the GDPR, how much time do you have to fulfill the data deletion after a member requested to do so?
I am not a lawyer by profession or preference, so I don't know. It all depends. There is a number, it changes, and so I cannot say anything that is exactly.
Consult your legal team.
Consult your legal team. Most of the guidance has been within reasonable time frames. So if someone says, delete my search history, and the page refreshes and their search history is right there and it's not gone, that's not okay. But if it's somewhere buried somewhere where it's no one's seeing it yet, and it's super hard to get rid of it, and you'll get rid of it within a reasonable time frame, that's okay.
Okay. So next one is, what are the main advantages of Gobblin compared to other tools?
Oh, well, well, that's
a long one.
That's a long one. I think there are a couple of things we've tried to do. We've tried to make sure that data, that it's not just thought of as an ETL tool where it has to do everything, including large-scale transformations and shuffles. It does a few things well, but it also makes sure that you can integrate. You can take a integration that you have in a batch world and then move to streaming, or take an integration that you have to do in a streaming world and move to batch. The other thing that we did was make sure that it can work in both kind of a single node, standalone environment, as well as in a highly scalable MapReduce environment. So there are a couple of those things that we did that we think make it stand out from a lot of other systems that we've worked with.
Okay. Next one is, do you have a separate team for adding metadata to the data sets, like some kind of pre-processing, or is this a responsibility of the data scientists as well?
Okay, great question. So, so what we've ended up doing is instilling this culture of ownership of data within the company. And the owner of a data set is, in a lot of cases, the producer of the data set. So if you're an engineer and you're producing a data set, then you own it. It doesn't matter whether you're a data scientist or you're a Java service builder, but you own it. And as a result, you have privileges on the data set. You can write to it. That makes you an owner. That means you have certain obligations to the data set as well.
With great power comes great responsibility.
Absolutely.
Something like that.
Yep.
All right, so the next one, have you considered hashing PII data and being able to remove the hash so the member is forgotten?
Yeah, we've considered it. There are some views that actually do this as well, but there are a lot of details. Like you have to be really careful that whatever you're leaving behind cannot be reconstructed to reconstruct the identity. There are some famous, there's the Netflix 23 bits thing. There are famous algorithms that can easily reconstruct identity and does not constitute true deletion. So check with your legal team about exactly what constitutes deletion. But having a central layer where you can, that's kind of what's been useful. Like if you have a central access layer and you have a way of applying transforms on the fly, then you don't have to worry so much about whether you got it right. If it changes, you can go in and fix it up, and then the next time it's going to be right. So build in agility in all of these layers, and then you can relax. Because if you decide to do it one way and then you have no way of changing that, then there's a problem.
Okay.
Cool.
How expensive is GDPR compliance in processing costs?
It's definitely very expensive in thinking cost. We've been thinking about it for a long time, and we've been in a lot of meetings, and we've sometimes calculated the cost of that as well. There have been a lot of slide decks created. But at the same time, a lot of times we put our, I guess, citizen hat on or our member hat on and think about the problem in that perspective. And we say, it's worth it to do this. And in some cases, if the cost is super high, then we talk to our legal team and say, hey, look, this technology was not ever meant for doing this. And the cost of doing it the way you would think the legal law implies is too high. And so do you think this meets kind of the justifiable need for not doing it? In some cases, we do get exceptions. So.
Okay. How do you manage the operations of all the data processing and implementation? Is there some super manager who knows about everything?
By super manager, I imagine you mean a super orchestrator, a data orchestrator of some sort. So right now we don't. We have different systems that people use. Some people use Azkaban directly to execute their workflows. Some people use a platform called UMP that actually Shrikant, my colleague, is going to talk about tomorrow for doing standardized reporting and analytics. And that thing is layered on top of Azkaban. So there's not one central super workflow orchestrator. But with a lot of the metadata work that we're doing, we're actually kind of building that graph of workflows and what they produce and how they consume it. And it actually leads to interesting future cases where we can turn that graph around into a workflow orchestrator. But we haven't kind of figure out if that's a cool thing to do or it's actually practical. It's definitely cool.
That sounds cool. All right, well, I think that's it for the questions.
Cool.
Thank you very much.
Thank you so much.
And let's give him a round of applause, please.
All right, thank you.